Chemistry time. Chemistry time. We're talking about, let's call this, we're going to title it Thermochemistry. I'm going to title it, when I put the video up, I'm going to title it Basic Thermochemistry. We're going to do kind of a cursory forest view of thermochemistry, focusing mostly on a simplified version of the math for two reasons. One, we've talked about some of this when we were in physical science, so we should already know some of this. And secondly, because you guys have read the content of this chapter, right? And you can, if you don't have the chapter, you can read about thermochemistry online pretty easily to understand the concepts. We will talk about the concepts as we go, but we're going to talk about them all in the framework of mathematics. So first of all, thermochemistry, first concept. What do you think we're talking about when we're talking about thermochemistry?
Radiate, like heat.
Heat, yeah. Thermo meaning heat in the Greek, right? Thermochemistry, so chemistry as it relates to heat. The first and most basic equation for thermochemistry that we're going to do is Q equals mc delta T. We're not going to spend a lot of time on this. In fact, we're going to spend very little time on this because, as I said, it's the most basic. You should already know it. And I also have on YouTube a video that you can watch where we talk about this at length. It's for physical science, but it's the same stuff, right? It describes each of these, what the quantities are, what they mean, and how we do it, what kind of units they have to be in. But just basically, Q here is heat. Q is the abbreviation we use for heat energy. M is mass. C is the specific heat of a substance. Delta is change in. Capital T is temperature. So if we multiply the mass of a substance times its specific heat times the amount of temperature change it endured, we get the heat that was released. And that leads us to the next thing. With this heat at a constant pressure, so the heat an object has, the thermal energy an object has at a constant pressure is called enthalpy, which we abbreviate, which we spell incorrectly, and then we abbreviate with the letter capital H. Enthalpy. You'll almost never see capital H enthalpy on its own. Where in your equations, what do you always see it with? You know, in every single equation that we have in our book, and every single equation we can do with it, we never see H equals anything. Or
yeah, it's like H with like a little, delta H.
There you go. Which means?
Heat.
You know it.
Enthalpy.
No, it's, change in
Enthalpy.
enthalpy. You were right, Helen. You said absorbed. It doesn't have to be absorbed, but it's how much it's either absorbed or released. And the reason for this is very, I think, interesting. Enthalpy, we can never directly measure how much heat something has. We know, for instance, that like the classic example is that a match head has a certain amount of heat, right?
Right.
Has a temperature, but that's something completely different. Separate temperature and heat in your mind. They're related, but they're not the same thing. So a match head has a certain amount of heat. Its atoms are moving at a certain rate and they're a certain distance apart. We know that the amount of heat in that match head, even though it has a higher temperature, is less than the total amount of heat in a swimming pool, for instance, just because there's more mass in the swimming pool. So if we add up all the motions of the particles in that, we get a larger number. But it's impossible for us to measure the exact amount of heat it has, because the particles are always moving. In fact, it relates to the Heisenberg uncertainty principle. We can't measure the speed and the position of all the particles that make something up, and so we can never actually measure how much enthalpy it has. But we can, and we do, measure the change in enthalpy. Okay? That's extremely important. So we can measure how enthalpy changes. Good so far? So we're always talking about the change in enthalpy. If enthalpy, delta H of negative is going to be, we talked about this already, so you know, negative delta H is going to be, for a process.
Absorption.
No.
Radiation.
Yeah, it's going to radiate. It's going to radiate heat, right? Its enthalpy is going to decrease in itself, which means in its environment, the enthalpy is going to increase, the heat is going to increase, and therefore we call that process what?
Release.
Yeah, when it releases heat into the environment, we call that?
Exothermic.
Exothermic. And then, of course, positive delta H is endothermic. Your book has an equation which I think is kind of funny. I'm not going to write it on the board, but it has an equation that says the universe equals the system plus its surroundings. And the reason they tell you that equation is that way you can tell that if the system is losing heat, the surroundings are gaining heat.
Right.
So basically what that means is that the system, the thing we're focusing on, is losing its energy, and so it must be going into the environment so that object would feel warm or would generate heat, which we call exothermic. I just think it's funny that they have, that's a simple definition of the universe, right? To a thermodynamicist, to a thermochemist, the universe is very simple. Universe equals system plus surroundings. That's like the definition itself is simple, but obviously if the book is my system and the surroundings is literally everything else in the universe, it gets pretty complex pretty fast, but it's just a kind of a fun, simplistic definition of the universe. So enthalpy is, or change in enthalpy, is how the heat is released or absorbed by the environment. We talk commonly about several different enthalpies, but we have something like, we call them all heat of blah, blah, blah. We have heat of combustion, which is how much energy, it's always released for combustion because you're never going to have a cold fire. How much heat is released by combustion. Heat of fusion, which is what we call it when something melts. Heat of vaporization. There are others. We have, if you see something that says like, calculate the heat of solution of this, and it gives you, you do it in the same way. You do the math in the same way as these. You just they have a different name. These are always going to be given to you in kilojoules per mole. Is the sign for delta H. And so if we're trying to calculate, for instance, if we say, these are pretty simple equations, but if we say we have 25 grams of ethanol, C2H3O2. If we have 25 grams of ethanol, that's not right, is it C2H3? Let's not say ethanol. Let's say something else. Let's say methane, because I can actually remember the formula for methane. 25 grams of methane, CH4. To convert it, to find out how much energy it would release, it's pretty easy. We just take 25 grams, convert grams to moles, and then from moles we convert to kilojoules using the standard enthalpy of combustion, which for methane happens to be negative 891. The grams per mole, 1 mole of methane would have 16 point something grams, and so for math we take 25 times negative 891, and then divide by 16, we're going to get a negative number. And what does the negative number here tell us? We don't need to actually do the math here, but the negative number tells us that this process is
releasing heat.
Yeah, it's releasing heat. It's exothermic. So if we were to burn 25 grams of methane, we would release this much heat. It's a pretty simple math situation. Do you have questions about that before we move on?
Nope.
Okay. And that's as far as really as we've gotten in the math that we've done together so far. But we're gonna start with the next thing, which is called Hess's law. So write this down. Hess is spelled H-E-S-S. Hess's is spelled that, but with apostrophe S. And now we're talking about Hess's law. And this is not erasing quite as well as I wish it was. Hess's law. Hess's law exists because for some reactions, physical or chemical, it's troubling to try and find how much heat is absorbed. So we know it's impossible to calculate total enthalpy, right? We know we can't do that at all for anything.
Right.
But even to find the change in enthalpy is difficult for some processes, for several processes. The example your book gives is that there's a certain enthalpy of formation that we call it for diamond, right? You know that diamonds can be formed inside of Earth when carbon, coal usually, is compressed, and heated up.
Yes.
It's impossible to measure the change in enthalpy for that in the lab. Obviously, we can't just make that. I mean, it's a little less impossible now than it always has been. But for that, we use something called Hess's law. And Hess's law just states, I'm going to read this to you. If you can add 2 or more thermochemical equations to find a final equation for the reaction, then the sum of enthalpy changes for the individual reactions is the enthalpy changes for the final reaction. So let's just write that down. Sum of enthalpy changes for component reactions is the enthalpy change for the total reaction. I've abbreviated reaction here, RXN, as we usually do. So for instance, the next example they use is, we know the enthalpy of formation of 594 kilojoules. This is going to be pretty sloppy penmanship because I'm looking and writing at the same time. But if we know that sulfur plus oxygen yields us SO2. Why is that unbalanced? Why are they putting 2 with all those? It doesn't matter. But anyway, this is the standard enthalpy of formation, meaning that when we combine the basic things that make this up, this is a known value. You can look up this value. Your book gives it to you. You'll look it up for when you take your test. And then we also know that SO2 plus O2 yields SO3, and that's unbalanced. 2SO2 plus 2SO3, there we go. I think that balances it, doesn't it? And that's why we have the 2's back here to answer my previous question. And we have a delta H of that of negative 198. Okay, so both of these values are known. This is something called the standard enthalpy of formation, sometimes written this way. So delta H, enthalpy, right, change in enthalpy. The little F stands for of formation, and this little degree sign, it's not really a degree sign, pay special attention to this, okay? This little circle up here, you see it, you see it, Hadley? You see the little circle? This thing means, we use the word standard, but it means per mole. That means we're talking about 1 mole of the substance. So a little F means how much it takes, how much heat it takes to make that thing, or what? Does it always take heat to make things? No. No? How much heat, then what?
It's released.
It is released when it is made. So the difference between delta H, standard enthalpy of formation, and just plain delta H is that this one means per mole, that's what the little circle means, and formation is the sub F. So according to Hess's law, what can I do with these two things to find my overall enthalpy of formation? Very simple mathematically.
Okay, can you say it again?
According to Hess's law, what can I do with these two things to find my overall enthalpy of formation? Let me phrase this in a way that this might be happening in like a laboratory. So say we're creating sulfur trioxide, SO3. Okay?
Okay.
We're using sulfur, elemental sulfur, and oxygen gas to make it. So we're taking elemental sulfur and combining with oxygen gas in a certain ratio to give us sulfur trioxide. We know the enthalpy of formation for sulfur dioxide, and we know the enthalpy of formation of sulfur trioxide given these two things. But we don't know plain old sulfur plus plain old oxygen to SO3. You see? We know these two things. They're known quantities.
Right.
But we're trying to find...
Do you subtract them?
Try one more time.
I did add
You
them.
add them. Good. So we add negative 594 plus negative 198, which gives us the delta H of the whole thing, the whole rinky-dink thing, is negative 792. We could have done the math. I mean, I'm just too lazy to actually add those up. Negative 792. This is easy. Or, I don't want to hurt your feelings. This should be easy, right? We just add these two dang numbers together.
Right.
Where it gets kind of complicated is that we have to make sure of a couple things. Ensure the moles in each, sorry, let me make that a little bit better. Ensure the coefficients in each equation match. So you might remember me stupidly, don't be so mean to yourself, you remember me stupidly saying at the beginning, why do they double all this, right? It's 2S plus 2O2 yields 2SO2. Now we know. I shouldn't have said that, it was stupid, but we know because the moles of SO2 here have to match the moles of SO2 here, right?
Right.
So since this one has to be balanced with 2SO2, we have to balance this one with 2SO2. So we double all of this.
Is that an H behind the negative 5, or what is that?
This is 94.
Okay.
When we double this whole thing, we also have to double this. Like if you look at the table of molar enthalpies of formation, which you can find it online too if you're watching this video, but if you look in your book, oh golly, I should have had this prepared. There's a table of molar enthalpies of formation on page.
Is it 590?
No, it's in the R's. It's R something.
Oh, it's in that.
Yeah. R. I'm so sorry. Here we go. R 11 on page 975. You'll find for sulfur dioxide, SO2, do you see what the molar enthalpy of formation is?
R. What?
Page 975, table R11, heat of formation. Do you see that? Standard enthalpy of formation. We're looking for sulfur dioxide. They're kind of in alphabetical order. No, next table. You see it says heat of formation? Yep.
Oh yeah, heat of formation values, okay.
For sulfur dioxide.
Which is SO4.
Nope.
SO2.
Yep.
Is negative 296.8.
Good. Negative 297. So why is this negative 594 then?
Because you add the oxygen. Wait, what?
No.
Oh.
So what this means, look here.
I don't know.
I'm going to illustrate this a little bit more clearly. When we find on the table, it just says this.
Yeah.
Okay? It doesn't say per mole.
There's two.
There we go.
There's
Look,
two.
now listen, Hadley. Hannah's about to get it.
There's
Say.
2 sulfurs and 4
Because,
oxygens.
like I said, because we had to double this
Yeah.
to make this match because of this. Ensure the coefficients in each equation match. Because we had to have a coefficient here, we had to double this. When we double this, we also have to double this. You'll notice that 2 times 297 is 594. Does that kind of make sense?
Yes.
So when we, step 1, make sure the moles match. So make sure the coefficients match. If they don't, make them. When you make them match, also do whatever you did to the standard enthalpy of formation, okay? When it says this is all the book tells us, right? When you look at the table, all it says is standard enthalpy of formation of SO2. It means to make it from its elements. It means S plus O2 yields SO2. That's it.
Okay.
So even though it doesn't say this, that's all implied when you look at this.
Okay.
Okay, so Hess's law, we just add them together. There's some little like bookkeeping things like this that we have to do when we add them together. And the other thing we have to watch out for is watch, put it in caps in your notes, watch them signs. I'm going to speak it like a cowboy. Watch them signs, right? Make sure that if you're adding a negative and a negative, the answer should be negative, and it should be bigger. If you're adding a negative and a positive, the answer should be, we don't really know what it's going to be, but it's going to be, make sure that you add them with their sign, okay? Here, this is expressed mathematically, it's this. And I like the way this looks. Like this is something you would want to have on your, like if you're doing a TV spot on an ad, and you want it to look like science is being done, you can write this equation. But it's basically just talking about what we just said. Uh-oh, I'm going to run out of room with my science words. Where'd my dang eraser go? All it's telling us is that for the total reaction, the enthalpy change per mole, where am I getting per mole from? Like what sign here means per mole?
H.
No. This circle. That little circle means per mole. Basically it allows us to use kilojoules throughout this whole thing instead of kilojoules per mole. Anyway, what it's saying is that the enthalpy change for the whole reaction is equal to the sum of the enthalpy of formation of the products plus the sum of the enthalpy change of formation of the reactants. It's exactly what we just did, but they put it in scary looking Greek letters so that it looks sciencey. It actually does mean something. This is really truly the most concise way to write it, but it also, doesn't that look so dang sciencey?
Yeah, it does like this.
Yeah, it looks so dang sciencey.
Because somebody's going to be like, what does any of that even mean? And you're going to be like,
And you're like, well, let me tell you, thermochemistry. And they're like, I don't know thermochemistry.
and you're like, well, learn it.
You're going to say, maybe you should go do a spelling. Last thing we're going to talk about, there is math to be done in the last lesson, but we're just going to talk about some like half conceptual, half math. And it is this, write down reaction spontaneity. Ooh, that sounds fancy too. All this sounds so fancy, but really, as you saw, what we just did is stuff you learned in the 5th grade, right? Adding together integers. It's not difficult. We just do it fancily. And it does have really important and...
Is there a lot more notes?
No. We do have really important, like, results of this. The reason we do it is important. And it's important to know about, but it's really not, I wouldn't say, difficult. So reaction spontaneity is great. Reaction spontaneity. What's spontaneity mean?
I have no idea.
What word is this related to, do you think?
Spontaneous.
Spontaneous. If your boyfriend's spontaneous, what's that mean? He likes to do what?
Like random things.
Wild crap, right?
Let's
Yeah.
just go
He's
to
like,
the
let's-
drive-in movie.
Let's go to the drive-in movie theater.
Right now.
Let's break into Mount Rushmore. Right?
Yeah. Let's steal some
Let's
jewelry.
kill a guy.
Let's kill a guy.
No. But spontaneous means happens, right? It just happens effectively for no reason. Reaction spontaneity, in chemistry, it means how likely a reaction is to occur on its own. How likely a reaction is to occur on its own. For instance, that diamond, well, that's not a good example, but it's technically the diamond forming from coal is a spontaneous process. Or maybe it's the other way around. Maybe the diamond switching itself into coal over time is spontaneous. But we're going to get into that not right this second. For instance, hydrogen peroxide decomposing into water and oxygen. That's a spontaneous process. It happens with no input. While we sit here doing nothing, the hydrogen peroxide I have in the laboratory is just decomposing into hydrogen and oxygen. So this process, H2O2, yields H2O plus O2. This is spontaneous. And we use the symbol, sorry, let me remind myself. Delta G. Delta G is called Gibbs free energy. Gibbs, named after a dude from Yale. Nice. Good job, Gibb. Gibbs free energy. And if delta G is positive, the reaction is non-spontaneous. And if delta G is negative, the reaction is yes spontaneous. So for this equation, hydrogen peroxide decomposing into water and oxygen gas, would the delta G be positive or negative? Well, we said it's spontaneous, even as we sit here doing nothing, putting in no input, delta G is negative. Delta G is negative. Gibbs free energy is calculated this way. Delta G, Gibbs free energy, change in Gibbs free energy, is the enthalpy minus the temperature in Kelvin times delta S. We're going to talk about delta S in a second. Where, make some more room, where delta G is Gibbs free energy, delta H, you know what delta H is. What's it?
Delta H is
F and
What? F?
change in enthalpy.
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 Change in enthalpy. Capital T is temperature. The temperature... Please forgive me. Delta T is temperature, which must be measured in this case in kelvins. And delta S is what we call entropy. Entropy is kind of a... I'm going to give you the thermodynamic definition. You've probably heard of entropy. You might hear it described as like the measurement of chaos or the opposite of energy. But your book defines entropy as a measure of the number of possible ways the energy can be distributed. Fair enough. For what we're going to do, for your test and for your chapter review, it'll be just like solving an equation you've ever done. Entropy change will be given to you. Enthalpy change will be given to you. You'll be given a temperature. You may have to convert. In fact, you usually must convert. You almost always have to convert in this equation because, let me read you exactly what the book is. To calculate Gibbs free energy, it is usually necessary to convert units because entropy is expressed in joules per Kelvin, whereas delta H is expressed in kilojoules. So this is in joules per Kelvin. Enthalpy is in kilojoules. Do you see how there's a disconnect there?
Yes.
Because joules and kilojoules. So one of them is going to have to be multiplied by 1,000 or the other divided by 1,000. And speaking of that, what's our unit for Gibbs free energy going to be? So if we have kilojoules minus Kelvin times joules per Kelvin,
Kilos.
yeah, well, it's going to be either kilojoules
Or joules.
or joules. It's just a measure of energy still. So we usually have to convert. You'll be given whichever ones of these you'll need. What else might you have to convert?
Maybe like the mass or something?
No, there's no mass in this one.
Kelvin to
Yeah,
something
you
else.
might be given degrees Celsius, but you might have to convert that to Kelvin. We went through kind of a lot. Do you have questions right now that you'd like to be on video? Because we'll talk about it here in a second if you have
No.
private questions. What's spontaneous mean? That
What
kind of
is
thing.
spontaneous mean?
Spontaneous means when something happens for no good reason. I don't know. That's not a great definition, but in chemistry, spontaneous means the reaction occurs without an input of energy. Thanks for the great question, Hadley. You guys have any other questions?